This week in physics, we're going to be talking about magnets and magnetism. Now, last week we were dealing with things like electricity, and eventually magnets and electricity are going to connect. But before we can start working with that, we need to go ahead and just establish some of the basics about how magnets work and talk about the fundamental properties of magnets. Now, to go ahead and get us started with, there are lots of different types of magnets that you might be seeing as we go through this thing. However, for the sake of this week, and we'll describe more later, we're just going to be dealing with two different types. There are permanent and there are temporary magnets. Now, a permanent magnet is exactly what it sounds like. It's a magnet that stays a magnet all the time. A temporary magnet, I'm going to go ahead and spell that correctly. There we go. A temporary magnet is a magnet that changes whether it is a magnet or not based on its circumstances. Now, it's easiest to talk about permanent magnets first. A permanent magnet, or any magnet in this case, is something that carries a fixed magnetic field around it. So it's something that generates a magnetic field. If I was to place a little magnet right here, and you were to do kind of a field test on it, you would see that it generates a magnetic field around it. And that allows it to influence certain things, like compasses. Normally I have a compass that faces north, but you can see as I kind of move it around, the magnet is telling this compass where north is instead of the Earth's magnetic field. And so that's an example of this specific magnet's magnetic field. So anything that carries a magnetic field with it is what we're going to be working with as a magnet. Now, some things hold that magnetic field permanently. Some things only have a magnetic field when you do specific things to it. Now, at this point, you probably realize that most magnets are made of metal or something similar to metal. This is a tiny thing. It's porcelain with iron in it. I have these bar magnets. This is mostly just mostly just iron. I've got this, which is hematite. It is a rock that has a lot of iron in it. It's just been polished into a ball shape. This right here is my strongest magnet, actually. This is from a magnetic element called neodymium. It's an alloy of multiple metals, and as you can see, it's extremely magnetic, to the point that it'll hold up all of the rest of these things if I give it a try. But they're mostly made of metals. Now, magnets in general are only created using iron, nickel, and cobalt. So we've got three specific metals that you should be looking for when you're looking for what can make a magnet. So kind of again, we're looking at iron, which the chemical symbol is Fe, nickel, chemical symbol Ni, and cobalt, chemical symbol Co. So those are going to be our three elements that we can possibly see when we're dealing with the types of elements when we're looking for what elements can create a magnet. Now, there's a couple of properties for magnets that we have to kind of be aware of, and this is going to sound really familiar to electricity. Last unit, when we talked about electricity, we talked about protons and electrons, positives and negatives. With magnets, all magnets have a side that is identified as being north and a side that is identified as being south. So we've got the north and the south poles of the magnet. So they're called magnetic poles. They always occur at the end of bar magnets, and they're always the same strength. So if I've got a north pole that is really, really strong, that means I have a south pole that is really, really strong. They always have to be equal. And if you're looking for the weakest point in a magnet, since the poles are the strongest, the weakest point is going to be the exact middle of the magnet. That is why the middle of the magnet doesn't actually stick to things very well. And basically it runs as kind of the closer you are to the pole, the stronger you are, and then as you work your way in, the weaker and weaker the magnetic bit gets. Now, I said that all magnets have a north and a south pole, which brings me to the question, what happens if I break a magnet? So, since I'm not actually going to break a magnet, I need to keep my magnets whole. Let's say that I have a bar magnet similar to the one that I just identified, and I have a north end and a south end. Okay, if I crack this thing down the middle, what happens is that I now have two magnets This is still the south end. This is still the north end. But that means this has now become the south end of that magnet, and this is going to become the north end of that magnet. So even if I break magnets in half, and I can do this 1,000 times until I'm just left with little pieces of magnetic dust, and each one of those pieces of magnetic dust still has a north and a south pole. So no matter what you do, you're always going to have this north and south, and it works kind of like with electricity where we had positive and negative. It's basically just the two different flavors that we're going to be dealing with for magnetism. Now, the Earth itself is a giant magnet. We have a rotating iron core in the middle of the planet that generates a magnetic field, and what that means is that it can influence other magnets, kind of like how my neodymium magnets right here are sticking to everything, and I can just kind of influence these and make them spin around and attach to each other. The Earth itself influences other magnets. So kind of going back to that idea of a compass, if I have a compass, compasses, if there aren't any other magnets nearby, naturally read Earth's magnetic field. So this compass is pointing towards magnetic north. It's somewhere over in that direction. And if I continue to kind of follow the compass, you'll eventually lead to magnetic north, which is not the North Pole. The magnetic North Pole of the United States, or of the Earth, sorry, migrates every once in a while. It's not a stable North Pole, but the compass will eventually take you there. And so that's kind of how compasses work, is that they're just simply reading the Earth's magnetic field. They are being influenced by Earth's magnetism. And we should be really happy that Earth is magnetic, because if it wasn't, we'd all be dead. Like most things in physics, you screw up one little thing and all of a sudden everything falls apart. Earth's magnetic field shields us from radiation, and that radiation, if it was allowed to go through, would just simply kill us. We'll talk about radiation in a couple of weeks. I'm going to go ahead and remove all of these magnets, because even having them off camera is making my, my compass go crazy. We've already done field lines. Good. So the one other thing that I want to really mention is that the strength of a compass, or sorry, the strength of a magnet is related to how far apart the magnets are. And it's similar to gravity. The closer that an object is to an object of really large mass, the stronger it gets. But I can place these two magnetic spheres apart from each other, and they just don't care. They're just rolling around. But the closer that I get them, the stronger that magnetism gets, until all of a sudden that force suddenly snags and they come together. So it gets exponentially stronger the closer you get. And so magnetism is one of those forces that it can act over a distance. It doesn't require contact, but it gets significantly stronger the closer that we are. So just kind of keep that in mind, that magnetism gets stronger as we get closer to other things. Now, the other thing that we're going to deal with this week is something called magnetic induction. Magnetic induction is what happens when I take something that isn't normally a magnet and I turn it into a magnet. So you can induce magnetism in a lot of ways, but I'm going to show you a really simple version that I can use as an example. So this right here is a construction nail, and as you can see, it is barely magnetic, very, very loosely. I can only just barely spin the compass. But what I can do is that I can induce magnetism in it by bringing it closer to another strong magnet. So I'm going to bring back my neodymium magnet. And if I kind of rub the neodymium magnet on the nail, what's happening is I'm aligning the particles that make up the nail so that they become magnetic just like the magnet. And now once I remove that magnet and I bring back my compass, now all of a sudden I'm able to influence that compass using the nail in a way that I wasn't able to do before. So now the nail is magnetized. It has been induced. So that's kind of a simple explanation for how magnetic induction works. Now, on a more complicated level, let's say I had, and I'm going to go ahead and clear my board here. Let's say I had the giant end of a magnet, and this was the north end of a magnet. If I stick something that doesn't normally have any magnetism to it next to that north end, it's going to induce a south end, which will then create a north end over here. So we induce the opposite pole, is the easiest way to explain it. So if I've got a north end, it's going to stick to something, and it does that because this is the south end. And just like with electricity, we're dealing with that same rule, and I'm sure that you've seen this with magnets before, but we're still dealing with that idea that opposites attract and likes repel. So if I've got a north and a north, they are not going to willingly go together. Or in this case, I can have a south and a south. They won't have anything to do with each other. North and north, same deal. So we're still dealing with opposites attract, so I can take my south side and my north side. They're perfectly fine connecting. So when you induce something, that same rule applies, and the opposites are going to kind of stick, or they're going to get away from each other, and the opposites will stick, and the similar ones will kind of get away from each other as much as they possibly can. Now, this iron nail right here is not a permanent magnet. If I wait for a little while, it's going to go back to being non-magnetic. Now, it's not going to happen during the course of this video. It'll hold on to it longer than that, but it's definitely not permanent. So what we refer to this is a soft magnet. A soft magnet is something that is easy to magnetize, but that magnetism is only temporary. Basically, we can switch it on and we can switch it off based on what's going on. So now that it's not next to another strong magnet, my magnet, or this nail, has gone back to kind of being a weak magnet, if it's a magnet at all. Now, kind of in opposition to that, if I go back to my neodymium magnet, this thing is going to be a magnet. It's going to be a magnet now. It's going to be a magnet tomorrow. It's still going to be a magnet when I am dead. This is a hard magnet. Hard magnets will keep their magnetism, and they make for excellent permanent magnets. They are not going to change their magnetism anytime soon. So we've got soft magnets, we've got hard magnets. We need to remember that our magnets always have poles. We've got our north and our south. And when we're dealing with that, we've got opposites attract and like charges repel. So those are kind of the basics of magnets. I have attached some additional information to Canvas. So if you want to figure out like what makes a magnet at a subatomic level, it's a little bit of quantum physics, which puts it outside of the realm of this course, but the videos that I have attached are very understandable. So if that's something you want to look at, go ahead. Otherwise, I will see you guys next week.